A controller area network is a vehicle bus standard designed to allow microcontrollers and devices to communicate with each other in applications without a host computer. It is a message-based protocol, designed originally for multiplex electrical wiring within automobiles, but is also used in many other contexts. Development of the CAN bus started in 1983 at Robert Bosch GmbH. The protocol was officially released in 1986 at the Society of Automotive Engineers conference in Detroit, Michigan. The first CAN controller chips, produced by Intel and Philips, came on the market in 1987. The 1988 BMW 8 Series was the first production vehicle to feature a CAN-based multiplex wiring system. Bosch published several versions of the CAN specification, and the latest is CAN 2.0, published in 1991. This specification has two parts. Part A is for the standard format with an 11-bit identifier, and Part B is for the extended format with a 29-bit identifier. A CAN device that uses 11-bit identifiers is commonly called CAN 2.0A, and a CAN device that uses 29-bit identifiers is commonly called CAN 2.0B. These standards are freely available from Bosch along with other specifications and white papers. In 1993, the International Organization for Standardization released the CAN standard ISO 11898, which was later restructured into two parts: ISO 11898-1, which covers the data link layer, and ISO 11898-2, which covers the CAN physical layer for high-speed CAN. ISO 11898-3 was released later and covers the CAN physical layer for low-speed, fault-tolerant CAN. The physical layer standards ISO 11898-2 and ISO 11898-3 are not part of the Bosch CAN 2.0 specification. These standards may be purchased from the ISO. Bosch is still active in extending the CAN standards. In 2012, Bosch released CAN-FD 1.0, a CAN with flexible data rate. This specification uses a different frame format that allows a different data length, as well as optionally switching to a faster bitrate after the arbitration is decided. CAN-FD is compatible with existing CAN 2.0 networks, and new CAN-FD devices can coexist on the same network with existing CAN devices. CAN bus is one of 5 protocols used in the onboard diagnostics 2 vehicle diagnostics standard. The OBD2 standard has been mandatory for all cars and light trucks sold in the United States since 1996, and the EOBD standard has been mandatory for all petrol vehicles sold in the European Union since 2001 and all diesel vehicles since 2004. Applications. Automotive. The modern automobile may have as many as 70 electronic control units for various subsystems. Typically, the biggest processor is the engine control unit. Others are used for transmission, airbags, anti-lock braking, ABS, cruise control, electric power steering, or audio systems, power windows, doors, mirror adjustment, battery and recharging systems for hybrid, electric cars, etc. Some of these form independent subsystems, but communications among others are essential. A subsystem may need to control actuators or receive feedback from sensors. The CAN standard was devised to fill this need. One key advantage is that interconnection between different vehicle systems can allow a wide range of safety, economy and convenience features to be implemented using software alone, functionality which would add cost and complexity if such features were hardwired using traditional automotive electronics. Examples include auto start, stop, Various sensor inputs from around the vehicle are collated via the CAN bus to determine whether the engine can be shut down when stationary for improved fuel economy and emissions. Electric park brakes. The hill hold functionality takes input from the car's tilt sensor and the road speed sensors via the CAN bus to determine if the car is stopped on an incline. Similarly, inputs from seat belt sensors are fed from the CAN to determine if the seat belts are fastened, so that the parking brake will automatically release upon moving off. Parking assist systems. When the driver engages reverse gear, transmission control unit can send a signal via the CAN to activate both the parking sensor system and the door control module for the passenger side door mirror to tilt downwards to show the position of the curb. The CAN bus protocol has been used on the Shimano-Di2 electronic gear shift system for road bicycles since 2009, and is also used by the Ansman and Banks systems in the direct drive motor. The CAN bus is also used as a field bus in general automation environments, primarily due to the low cost of some CAN controllers and processes. Manufacturers including NISMO aim to use CAN bus to recreate real-life racing laps in the video game Gran Turismo 6 using the game's GPS data logger function, which would then allow players to race against real laps. Architecture. CAN is a multi-master serial bus standard for connecting electronic control units, also known as nodes. 2 or more nodes are required on the CAN network to communicate. The complexity of the node can range from a simple I/O device up to an embedded computer with a CAN interface and sophisticated software. The node may also be a gateway, allowing a standard computer to communicate over a USB or Ethernet port to the devices on a CAN network. All nodes are connected to each other through a 2-wire bus. The wires are 120 ohms nominal twisted pair. ISO 11898-2, also called high-speed CAN, uses a linear bus terminated at each end with 120 ohms resistors. ISO 11898-3, also called low-speed fault-tolerant CAN, uses a linear bus. Star bus. A multiple star bus is connected by a linear bus and is terminated at each node by a fraction of the overall termination resistance. The overall termination resistance should be about 100 ohms but not less than 100 ohms. High-speed CAN is usually used in automotive and industrial applications where the bus runs from one end of the environment to the other. Fault-tolerant CAN is often used where groups of nodes need to be connected together. The ISO specifications require the bus be kept within a minimum and maximum common mode bus voltage, but do not define how to keep the bus within this range. Each node requires a central processing unit, microprocessor, or host processor. The host processor decides what the received messages mean and what messages it wants to transmit. Sensors, actuators and control devices can be connected to the host processor. CAN controller, often an integral part of the microcontroller receiving. The CAN controller stores the received serial bits from the bus until an entire message is available, which can then be fetched by the host processor. Sending. The host processor sends the transmit message to a CAN controller, which transmits the bits serially onto the bus when the bus is free. Transceiver defined by ISO 11898-2/3 medium access unit standards. Receiving. It converts the data stream from CAN bus levels to levels that the CAN controller uses. It usually has protective circuitry to protect the CAN controller. transmitting. It converts the data stream from the CAN controller to CAN bus levels. Each node is able to send and receive messages, but not simultaneously. A message frame consists primarily of the ID, which represents the priority of the message, and up to 8 data bytes. A CRC, acknowledge slot and other overhead are also part of the message. The improved CAN-FD extends the length of the data section to up to 64 bytes per frame. The message is transmitted serially onto the bus using a non-return-to-zero format and may be received by all nodes. The devices that are connected by CAN network are typically sensors, actuators, and other control devices. These devices are connected to the bus through a host processor, a CAN controller, and a CAN transceiver. A terminating bias circuit is power and ground provided together with the data signaling in order to provide electrical bias and termination at each end of each bus segment to suppress reflections. Data transmission. CAN data transmission uses a lossless bitwise arbitration method of contention resolution. This arbitration method requires all nodes on the CAN network to be synchronized to sample every bit on the CAN network at the same time. This is why some call CAN synchronous. Unfortunately, the term synchronous is imprecise since the data is transmitted without a clock signal in an asynchronous format. The CAN specifications use the terms dominant bits and recessive bits, where dominant is a logical 0 and recessive is a logical 1. The idle state is represented by the recessive level. If one node transmits a dominant bit and another node transmits a recessive bit, then there is a collision and the dominant bit wins. This means there is no delay to the higher priority message, and the node transmitting the lower priority message automatically attempts to retransmit 6-bit clocks after the end of the dominant message. This makes CAN very suitable as a real-time prioritized communications system. The exact voltages for a logical 0 or 1 depend on the physical layer used, but the basic principle of CAN requires that each node listens to the data on the CAN network, including the data that the transmitting node is transmitting. If a logical 1 is transmitted by all transmitting nodes at the same time, then a logical 1 is seen by all of the nodes, including both the transmitting node and receiving node. If a logical 0 is transmitted by all transmitting nodes at the same time, then a logical 0 is seen by all nodes. If a logical 0 is being transmitted by one or more nodes, and a logical 1 is being transmitted by one or more nodes, then a logical 0 is seen by all nodes, including the node transmitting the logical 1. When a node transmits a logical 1 but sees a logical 0, it realizes that there is a contention and it quits transmitting. By using this process, any node that transmits a logical 1 when another node transmits a logical 0 drops out or loses the arbitration. A node that loses arbitration requeues its message for later transmission, and the CAN frame bitstream continues without error until only one node is left transmitting. This means that the node that transmits the first one loses arbitration, since the 11-bit identifier is transmitted by all nodes at the start of the CAN frame. The node with the lowest identifier transmits more zeros at the start of the frame, and that is the node that wins the arbitration or has the highest priority. For example, consider an 11-bit ID CAN network, with two nodes with IDs of 15 and 16. If these two nodes transmit at the same time, each will first transmit the start bit, then transmit the first 6 zeros of their ID with no arbitration decision being made. When the 8th bit is transmitted, the node with the ID of 16 transmits a 1 for its ID, and the node with the ID of 15 transmits a 0 for its ID. When this happens, the node with the ID of 16 knows it transmitted a 1, but sees a 0 and realizes that there is a collision and it lost arbitration. Node 16 stops transmitting, which allows the node with ID of 15 to continue its transmission without any loss of data. The node with the lowest ID will always win the arbitration, and therefore has the highest priority. Bit rates up to 1 mbit per second are possible at network lengths below 40 meters. Decreasing the bitrate allows longer network distances. The improved CON/FD standard allows increasing the bitrate after arbitration and can increase the speed of the data section by a factor of up to 8 of the arbitration bitrate. ID allocation. Message IDs must be unique on a single COM bus. Otherwise, two nodes would continue transmission beyond the end of the arbitration field, causing an error. In the early 1990s, the choice of IDs for messages was done simply on the basis of identifying the type of data and the sending node. However, as the ID is also used as the message priority, this led to poor real-time performance. In those scenarios, a low COM bus utilization of circa 30% was commonly required to ensure that all messages would meet their deadlines. However, if IDs are instead determined based on the deadline of the message, the lower the numerical ID and hence the higher the message priority, then bus utilizations of 70 to 80% can typically be achieved before any message deadlines are missed. Bit timing. All nodes on the CON network must operate at the same nominal bit rate, but noise, phase shifts, oscillator tolerance and oscillator drift mean that the actual bit rate may not be the same as the nominal bit rate. Since a separate clock signal is not used, a means of synchronizing the nodes is necessary. Synchronization is important during arbitration since the nodes in arbitration must be able to see both the transmitted data and the other node's transmitted data at the same time. Synchronization is also important to ensure that variations in oscillator timing between nodes do not cause errors. Synchronization starts with a hard synchronization on the first recessive to dominant transition after a period of bus idle. Resynchronization occurs on every recessive to dominant transition during the frame. The CON controller expects the transition to occur at a multiple of the nominal bit time. If the transition does not occur at the exact time the controller expects it, the controller adjusts the nominal bit time accordingly. The adjustment is accomplished by dividing each bit into a number of time slices called quanta, and assigning some number of quanta to each of the 4 segments within the bit. Synchronization, propagation, phase segment 1 and phase segment 2. The number of quanta the bit is divided into can vary by controller, and the number of quanta assigned to each segment can be varied depending on bitrate and network conditions. A transition that occurs before or after it is expected causes the controller to calculate the time difference and lengthen phase segment 1 or shorten phase segment 2 by this time. This effectively adjusts the timing of the receiver to the transmitter to synchronize them. This resynchronization process is done continuously at every recessive to dominant transition to ensure the transmitter and receiver stay in sync. Continuously resynchronizing reduces errors induced by noise, and allows a receiving node that was synchronized to a node which lost arbitration to resynchronize to the node which won arbitration. Layers. The CON protocol, like many networking protocols, can be decomposed into the following abstraction layers: application layer, object layer, message filtering, message and status handling. Transfer layer. Most of the CAN standard applies to the transfer layer. The transfer layer receives messages from the physical layer and transmits those messages to the object layer. The transfer layer is responsible for bit timing and synchronization, message framing, arbitration, acknowledgement, error detection and signaling, and fault confinement. It performs fault confinement, error detection, message validation, acknowledgement, arbitration, message framing, transfer rate and timing, information routing. Physical layer CAN bus originally specified the link layer protocol with only abstract requirements for the physical layer, e.g., asserting the use of a medium with multiple access at the bit level through the use of dominant and recessive states. The electrical aspects of the physical layer were specified in ISO 11898-2/2003, which is now widely accepted. However, the mechanical aspects of the physical layer have yet to be formally specified. As a result, an automotive ECU will typically have a particular or often custom connector with various sorts of cables, of which two are the CAN bus lines. Nonetheless, several de facto standards for mechanical implementation have emerged, the most common being the 9-pin D subtype male connector with the following pin out, pin 2, CAN low, pin 3, GND, pin 7, CAN high, pin 9, CAN V+. This de facto mechanical standard for CAN could be implemented with the node having both male and female 9-pin D sub-connectors electrically wired to each other in parallel within the node. Bus power is fed to a node's male connector and the bus draws power from the node's female connector. This follows the electrical engineering convention that power sources are terminated at female connectors. Adoption of this standard avoids the need to fabricate custom splitters to connect two sets of bus wires to a single D connector at each node. Such non-standard wire harnesses that join conductors outside the node reduce bus reliability, eliminate cable interchangeability, reduce compatibility of wiring harnesses, and increase cost. The absence of a complete physical layer specification freed the CAN bus specification from the constraints and complexity of physical implementation. However, it left CAN bus implementations open to interoperability issues due to mechanical incompatibility. Noise immunity on ISO 11898-2/2003 is achieved by maintaining the differential impedance of the bus at a low level with low-value resistors at each end of the bus. However, when dormant, a low-impedance bus such as CAN draws more current than other voltage-based signaling buses. On CAN bus systems, balanced line operation, where current in one signal line is exactly balanced by current in the opposite direction in the other signal, provides an independent, stable 0 volts reference for the receivers. Best practice determines that CAN bus balanced pair signals be carried in twisted pair wires in a shielded cable to minimize RF emission and reduce interference susceptibility in the already noisy RF environment of an automobile. ISO 11898-2 provides some immunity to common mode voltage between transmitter and receiver by having a 0 volts rail running along the bus to maintain a high degree of voltage association between the nodes. Also, in the de facto mechanical configuration mentioned above, a supply rail is included to distribute power to each of the transceiver nodes. The design provides a common supply for all the transceivers. The actual voltage to be applied by the bus and which nodes apply to it are application-specific and not formally specified. Common practice node design provides each node with transceivers which are optically isolated from the node host and derive a 5 volts linearly. regulated supply voltage for the transceivers from the universal supply rail provided by the bus. This usually allows operating margin on the supply rail sufficient to allow interoperability across many node types. Typical values of supply voltage on such networks are 7 to 30 V. However, the lack of a formal standard means that system designers are responsible for supply rail compatibility. ISO 11898-2 describes the electrical implementation formed from a multi-dropped single-ended balanced line configuration with resistor termination at each end of the bus. In this configuration, a dominant state is asserted by one or more transmitters, switching the CAN- to supply 0 volts and switching CAN+ to the +5 V bus voltage, thereby forming a current path through the resistors that terminate the bus. As such, the terminating resistors form an essential component of the signaling system and are included not just the limit wave reflection at high frequency. During a recessive state, the signal lines and resistor remain in a high impedances state with respect to both rails. Voltages on both CAN+ and CAN- tend towards the voltage midway between the rails. A recessive state is only present on the bus when none of the transmitters on the bus is asserting a dominant state. During a dominant state, the signal lines and resistor move to a low impedance state with respect to the rails so that current flows through the resistor. CAN+ voltage tends to +5 V and CAN- tends to 0 V. Irrespective of signal state, the signal lines are always in low impedance state with respect to one another by virtue of the terminating resistors at the end of the bus. This signaling strategy differs significantly from other balanced line transmission technologies such as RS-422/3, RS-485, etc., which employ differential line drivers, receivers and use a signaling system based on the differential mode voltage of the balanced line crossing a notional 0 V. Multiple access on such systems normally relies on the media supporting 3 states and is dealt with in the time domain. Multiple access on CAN bus is achieved by the electrical logic of the system supporting just 2 states that are conceptually analogous to a wired or network frames. A CAN network can be configured to work with 2 different message formats: the standard or base frame format and the extended frame format. The only difference between the 2 formats is that the CAN base frame supports a length of 11 bits for the identifier, and the CAN extended frame supports a length of 29 bits for the identifier, made up of the 11-bit identifier and an 18-bit extension. The distinction between CAN base frame format and CAN extended frame format is made by using the Id bit, which is transmitted as dominant in case of an 11-bit frame, and transmitted as recessive in case of a 29-bit frame. CAN controllers that support extended frame format messages are also able to send and receive messages in CAN base frame format. All frames begin with a start of frame bit that denotes the start of the frame transmission. CAN has 4 frame types: data frame, a frame containing no data for transmission; remote frame, a frame requesting the transmission of a specific identifier; error frame, a frame transmitted by any node detecting an error; overload frame, a frame to inject a delay between data and or remote frame. Data frame. The data frame is the only frame for actual data transmission. There are 2 message formats: base frame format with 11 identifier bits, extended frame format with 29 identifier bits. The CAN standard requires the implementation must accept the base frame format and may accept the extended frame format, but must tolerate the extended frame format. Base frame format. The frame format is as follows. The bit values are described for CAN-low signal. Extended frame format. The frame format is as follows. The two identifier fields combine to form a 29-bit identifier. Remote frame. Generally, data transmission is performed on an autonomous basis with the data source node sending out a data frame. It is also possible, however, for a destination node to request the data from the source by sending a remote frame. There are two differences between a data frame and a remote frame. First, the RTR bit is transmitted as a dominant bit in the data frame, and secondly, in the remote frame there is no data field, i.e. RTR equals 0, dominant in data frame. RTR equals 1, recessive in remote frame. In the event of a data frame and a remote frame with the same identifier being transmitted at the same time, the data frame wins arbitration due to the dominant RTR bit following the identifier. Error frame. The error frame consists of two different fields. The first field is given by the superposition of error flags contributed from different stations. The following second field is the error delimiter. There are two types of error flags. Active error flag. 6 dominant bits transmitted by a node detecting an error on the network that is in error state. Error active. Passive error flag. 6 recessive bits transmitted by a node detecting an active error frame on the network that is in error state. Error passive. Overload frame. The overload frame contains the 2-bit fields overload flag and overload delimiter. There are two kinds of overload conditions that can lead to the transmission of an overload flag. The internal conditions of a receiver, which requires a delay of the next data frame, or remote frame. Detection of a dominant bit during intermission. The start of an overload frame due to case 1 is only allowed to be started at the first bit time of an expected intermission, whereas overload frames due to case 2 start 1 bit after detecting the dominant bit. Overload flag consists of 6 dominant bits. The overall form corresponds to that of the active error flag. The overload flag's form destroys the fixed form of the intermission field. As a consequence, all other stations also detect an overload condition and on the part start transmission of an overload flag. Overload delimiter consists of 8 recessive bits. The overload delimiter is of the same form as the error delimiter.